Hello again and welcome. The video today is in response to a number of viewers that have watched the previous video all about that valve preamp. It was going to be part of the original video, but like most of my videos it got a bit bogged down with bits and pieces, so I omitted it from the video. This video is basically that. It's an in-depth analysis of the circuit, explaining what the components do, and my colleague in America, Ron, is going to provide the narration to this, and I just press the buttons to make it look reasonable so that you can see what's going on. I will warn you that it is quite technical and may not be to everyone's taste. So if our satellite link with Telstar is up and active, hello Ron, and it's over to you.
This is the schematic simplified for the entire preamp. It only shows one channel, and if you look at schematics that you find from other sources, you'll find that it's substantially the same. Some of the resistor values have changed here and there, but it's pretty much the same. This is the filament and LED section. They've made a pretty good attempt to put DC to the heaters of the two valves, which is a good idea. The R25 does cut down the voltage slightly from the peak rectified voltage, but not a great deal. It is half-wave rectified, obviously, through D3. Then they have the obligatory LEDs. Mine, by the way, did not work from the kit as supplied. I had to use different ones. And R11 and R7, I had to go to 1K resistors. By the way, all part numbers in these discussions are arbitrary. Now let's look at the power section. This is actually, to me anyway, the most interesting part of the entire board. It has several sections to it, and if you see what's going on here, let's zoom in on just the positive rail. The negative rail works exactly the same, but let's just zoom in on the positive rail. Here is just the positive rail for clarity. We don't need the clutter of seeing the negative rail at the same time. And as you can see, it's at first glance rather complicated, but if you break it down into its component parts, it's actually pretty simple. The input section consists of, in this nomenclature, C6, D1 and D7, and C10. It's a pretty much standard Cockcroft-Walton voltage doubler. There's nothing magic about it. Basically, on the negative half cycle, that's AC1 being more negative than AC2, it charges up C6, and then on the positive side, C6 adds to the positive voltage, goes through D7 and charges up C10 to approximately twice the peak voltage of the AC coming in. The next section is a pretty much classic standard capacitance multiplier. It does the job. It does take out a lot of the ripple, but not all of it, for a couple of reasons. First of all, because it cannot, C11 cannot really source any current through R10 and then on through the circuit, through the diode junction. If the incoming voltage drops below what the output emitter voltage is of Q3, it's just simply going to drop. That's all there is to it. It will, however, filter out peak or high transient voltages because of the R9 C11 filter. The next section is a current limiter. It operates to limit the amount of current that can pass through Q3 onto the output filter. It does this, of course, by having a resistor R12, which is 47 ohms, between the base and emitter of Q5. And of course, once the current reaches the threshold, switch threshold of Q5, it begins to clamp the drive to Q3, which is why R10 is 1K and not a direct connection, as would be the case in a true capacitance multiplier or classic capacitance multiplier. This, however, does limit the current coming out of it to, many sources say 10 milliamps, and it's really more like 12 milliamps. Why this is even needed in this circuit is sort of questionable, but there it is. Finally, this feeds an output filter consisting of R13 and C13, but notice that it's 47 ohms. The time constant in this is really rather short. So what in effect happens is, because of the time constants going all the way through this circuit, you do get a substantial amount of ripple on both the positive and negative rails, and there isn't much these circuits can do about it, to be quite honest. The problem is that the voltage doubler puts half-wave peaks on the input filter capacitors. This is only a half-wave rectifier, any way you look at it. So that alone means that there's going to be a lot of ripple. The capacitance multiplier doesn't really do much of anything for reasons I explained before. Again, the current limiter, we don't know why it's there. And the output filter, well, it's there, but it doesn't do much. Here is a close-up look at one channel. They're both identical. This is basically how it works. You have the volume control on the input, R16, or at least half of it. It is a linear, as Mike has mentioned. You have an isolation capacitor, C7, which is fairly substantial, 1 microfarad. R1 limits grid currents from flowing, peak currents that is, of course, because it's AC coupled. R2 provides a bias to the negative rail, not to common or ground. There's a reason for this. R6 is essentially a cathode bias resistor. Past that, the pentode is actually wired as a triode in this case. R28 is the anode resistor, and that feeds C8 to the output, which isolates the voltage, which we'll get to in a moment. And then you have R27, which is kind of a DC restoration resistor. It makes sure that the output is essentially at 0 volts. This is what happens when the unit is sitting there with no signal input. This is the quiescent voltage, or in semiconductor equivalent, the QI condition. Basically, you have minus 27.7 volts on the grid, which is pretty close to, as you can see, the negative supply of 27.74 negative. You notice that the cathode resistor is set at minus 27.41. That's because there is current flowing through R6, about 1.5 milliamp. And per the note you can see on the screen, it's not exactly equal to the anode current, but it's within measurement tolerances and resistance tolerances and so forth. Okay, then you have the plate current flowing down from the positive, approximately the same voltage as the negative, about another 1.5 milliamp flowing down. You end up with about 20.82 volts on the output, blocked by C8, and then headed out. Now this again is with no signal whatsoever. You may be wondering, why is the grid, the control electrode if you will, more negative than the cathode? This doesn't seem right. In semiconductor terms, that doesn't make any sense at all. But for a valve, it makes perfect sense, because if you simply took the grid, this is pin 1, and connected it to pin 7, the valve would turn on completely. It would just act as a diode, a rectifier, and it would be completely turned on or very close to it. Okay, so what you actually have to do to turn it off slightly, or to get it into a linear, hopefully, range, is to actually make the grid more negative than the cathode. The way they do that is because of the current flowing through R6. That's why it's there. In the old days, the bad old days, they used to actually put a battery in there, typically about 1.5 volts, and that was called a B voltage battery. And its purpose was to shut off the valve at quiescent conditions. Although it works, there's a little problem here. You notice that there is only about 0.29, less than 0.3 of a volt, to shut it off. That means that the maximum signal you're going to be able to put into this thing before it starts running out of room is about 0.3 volts. That's peak, by the way. So about 0.2 volts roughly. That's not a lot of dynamic range available, I'm sad to say. That corresponds to only a little over 2 volts peak, or about, let's say, 1.4 volts RMS output. That's the entire dynamic range of this amplifier, despite having plus and minus 27.7 volts available. That's a whole different world to semiconductor or op-amp based amplifiers. Here for reference is an excerpt from a 6J1 valve, or tube if you wish, spec sheet. There's some very interesting things on here. For one thing, notice that the anode current This is a typical value. It's 5.35 milliamps. We're running it at 1.45, 1.5, somewhere in there, milliamps, quiescent. Once again, that means you're off to the side a little bit of the ideal center point, which would be about 2.5 milliamps. So it limits the dynamic range. And there are some other things here that are kind of interesting, at least to me. Note that the input resistance is not infinite, as some people would say. It is actually rather low, 12 to 25 kiloohms according to this spec sheet, which I suspect is, remember, this is an RF valve. So this is probably at frequency. It's an impedance more than just a resistance. If you actually measure this with an ohm meter, you'll find that it does measure infinite, but at frequency, no. Finally, there's an interesting operational note. It is an inverting amplifier. And you look at it and you think, well, why is this? Does this actually make sense? Well, yeah, it does, because as the grid goes more positive, or the input signal actually goes more positive, the valve conducts harder, more, okay, as we explained before, because it should be negative to cut the valve off, to cut the conductance of the valve off. So what happens is it conducts more, pulls the output resistor down, so it's exactly the opposite. So in fact, it is an inverting amplifier. Thank you very much for watching.
Thanks very much, Ron. Now, I hope you're all listening there, because I should be asking questions later to see how much of that you've absorbed. On a final point, the circuit is what it is. We don't propose to do any modifications to it. There's a few people on the internet you'll find that have done the odd bodge here and there to try and get a bit of better performance out of it. But it is what it is. Build one, you'll enjoy building it and even listen to it. But it's not really a serious contender for hi-fi. So on that note, toodaloo, see you all soon.